So last time we described some basic aspects of geometry in 3 dimensions. We also discovered how hard it is to draw in 3 dimensions, right? I mean, instead of saying that I'm not really a really good artist here, so yeah. I mean, it's, of course, I'm not expecting you to draw 3D maybe later on, but the solids will be a lot easier to draw. You will see like some inclined planes, well, you will see later. But in the meantime, let's again describe some formula that we learned back in plane geometry, in plane analytic geometry, and to extend them to the 3D space, And we already talked last time about the distance formula. Well, add one more term inside of the radical for the z coordinate. For the midpoint formula, add one more average for the z values to get the midpoint, and for the sphere, add one more term in terms of z to make it a 3D. Ultimately, a sphere is a circle, a rotated circle. It's a sphere. Well, to put this in practice, actually we're gonna use all these three formulas together. Let's find the equation of the sphere given the points 0, 4, -3, and 2, 1, 0. All right, but in this case, those given points are the endpoint of the sphere, right? Or the endpoints of the diameter of the sphere. Okay, so number one, so there's two elements that we need to find the equation of the sphere in a similar way that there were for the circle, the center, and the radius. Same thing for the sphere. The sphere has a center and also has a radius. But in this case, these 2 points are not going to describe the radius, but the diameter. Let's find the diameter by finding, or rather the center first, by finding the midpoint of this sphere. So M, which is the midpoint, all we do is 0 plus 2 over 2, comma, then we go with the y's, 4 plus 1 over 2, and -3 plus 0 over 2, and that will simplify to, well, 0 plus 2 is 2 over 2, that's 1, comma, 5 halves, comma, -3 halves. All right, so that's the center of the sphere. The other piece of information that we need here is, to get the radius, we need to find out the diameter first, and then all we do is simply divide by 2, because that's what the radius is. Okay, so the distance right here, let's call it dpq. That's to denote that this is a distance. Well, square root of the difference between the x's squared plus the difference between the y's squared plus the difference between the z's squared. So let's go ahead. 2 minus 0, 1 minus 4, and 0 minus -3. And careful with signs, the smile rule will be needed here as well. So, well, let's find the diameter. So 2 minus 0, that's 2 squared, which is 4. 1 minus 4, that's -3. But -3 squared becomes positive 9, and 3 squared, that's another 9. All right, that adds up to the square root of 22. Okay? But note, this is the diameter. And for the circle, we don't want the diameter, we want the radius. And the radius will be then 1/2 of the diameter, which is 1/2 the square root of 22. Well, this is not going to simplify to a nice number like a nice integer, but still, okay, let's write the equation of the sphere in the same way that we wrote the equation for a circle. That's going to be x minus the x coordinate of the center, which is 1, quantity squared, plus y minus 5 halves, which is the y coordinate of the center, but in this case for the sphere we add one more piece of information, which in this case is plus x minus negative 3. Be careful here, that becomes plus 3/2 squared, and equals the radius quantity squared, but be careful when squaring this. So that's
the last one should be z, right? X
should be z, yeah. I don't know, yeah. And so that's going to be, okay, 1/4. And the square root of 22 squared, that's just 22, which reduces to 11/2. All right? And let's write this a lot nicer. X minus 1 11/2. Okay, I don't know why I get this box right here. Okay. So that's one example. I mean, in the same example, we use the 3 formulas. And well, so today we move on to vectors in space. And well, there's nothing new from what we learned last time about the vectors, adding and subtracting vectors and multiplying by scalars. All we're really going to do as new is add a third component for the vector to make it three-dimensional. And well, when it comes to writing vectors as linear combinations of the special unit vectors ij, well, the third component is the k vector. Okay. So, and well, the properties are exactly the same. The distances are the same. The calculations are the same. We just do it 3 times. Once for the x component, the second for the y component, and third for the z component. So we're given a couple of points, P and Q, and in this case we're given these points not as an order pairs, but rather as order triples. So let's write down AB, the vector AB in both component form and also as a linear combination of the special unit vectors I, J, and K. And well, to find the vector, to describe the vector AB, recall that all we do is, careful. One thing to note, because again, if you saw the question like this, it really wouldn't make sense, or it would make it ambiguous, because we need to be specific about which point is the initial, which point is the terminal. So initial and terminal. Also, or you know what? Actually, if it's not specific which one is which, we could go in alphabetic order. P goes first, Q goes afterwards. So AB. Well, so to write down the vector, subtract 0 minus 2. That's going to give us a -2. -1 minus -4. Isn't that 3? And 3 minus 6 is -3. All right, but they're asking us to write the vector in component form, but also as a linear combination of the special unit vectors I, J, and K. And notice again, notice about the notation. When we see these symbols type, they are in bold case, but when we write them, that's -2I with a hat at the top, plus 3j, that's to denote that these are the special unitized vectors. All right, and that's the answer. So same as the other vectors in 2 dimension, only one more component. Find the magnitude, same formula. It's the sum of the squares of the square root of the squares of the components. But in this case, we add the third component. So, and we denote the magnitude with a double bar. I believe our textbook uses one single bar. Or But it's important to keep in mind all different ways to denote this. So just square the numbers. Okay, that's the square root of 4 plus 9 plus 9. Oh, it's the same as before. Square root of 22. So this vector is square root of 22 units long. All right. We also discussed about unit vectors in last time's lecture. The way we find unit vectors in 3 dimensions is exactly the same. Divide the components of the vector that we already found by the magnitude. So, and well, we have a special notation for the unit vector, v with a hat, and that's the vector AB divided by its magnitude. And in this case, the vector we got, that's negative 2, 3, negative 3, divided by the magnitude, which is the square root of 22. And well, so we need to, in a way, distribute this denominator to each component. So that'll be negative 2 over root of 22, comma, 3 over root of 22, and negative 3 over root of 22. But that's not the only way to write a vector like this. Of course, we can use the IJK notation, that is the linear combination of the special unit vectors, that is negative 2 over root of 22 in the direction of I, plus 3 over root of 22 in the direction of J, and minus 3 over the square root of 22 in the direction of J. And well, the reason I write both is because, well, on the homework or on the exam you may be asked for one version or the other, or maybe even both. In some cases, my MATLAB exercises has a blank with this angular parenthesis and the 3 components. In some cases, you have 3 blank spaces, one multiplying the letter I, another blank multiplying the letter J, etc. Yes?
Instead of K, can we use Z?
Z would be for like points in this case, but the letter K is used for the vector because they go in alphabetic order for I, J, and K for the unit vector, special unit vector notation. Okay, a very typical problem in vectors is find a vector W, a new vector, brand new vector, in the same direction as the given vector that we found that passed through the 2 given points, but in this case has a length of 3. All right. Let's define that vector W. Okay, this vector that we just found in the previous part. What's the length of that vector? What's the magnitude of that vector? Because it's a unit vector, isn't it? So what would you do to obtain a vector? I mean, this vector right here, which can, well, the original vector, negative 2, 3, negative 2, negative 3 rather, is basically this vector, right? If we divide by its magnitude, we get a unit vector. This vector in red has a length of 1 and it's also going in the same direction as the given vector. But now, what would we do to get a vector that has a length of 3 starting with this vector? Multiply by 3, all right? That's what we would do. So this would be 3 times the vector v, which is 3 times negative 2 over root of 22, 3 over root of 22, comma, negative 3 over root of 22. And we'll just distribute this 3 in the numerators. Negative 6 over root of 22, positive 9 over root of 22, and negative 9 over root of 22. All right?
How can you tell whether it's asking you to reference the original vector AB or the unit vector?
So, for example, if we didn't go through, that's a good question because the My MATLAB homework will have they will give you a couple of points and ask you directly this question without first asking you to get a unit vector. So we would first need to get a unit vector and then multiply by the desired length, in this case 3, or if it's a length of 4, we'll multiply by 4, whatever length they would be asking us to multiply by, right? All right, so, okay, another definition that's the same as in vectors in 2 dimensions. 2 vectors in 3D are also the same if their components are equal. So, there's a little typo here, a misspell here. Well, 2 non-zero vectors u and v are parallel if there is some scalar c such that u equals c. In other words, it's a multiple of a vector. We already did one like this in the previous section. If we have like a common factor and it looks like a vector that we have to compare it with, well then these are parallel vectors. Alright, so let's have a look at one more example. So we have another vector whose initial point is a1, -2, -3, and terminal point b2, 1, 3. So they're asking us whether the vector v3, -3, 9, -9 is parallel to u. Well, we're given vector v, but we don't know vector u. However, we have the information to obtain vector u. So in this case, what we do to find vector u is subtract the components terminal minus initial vector u, and that's 2 minus 1, that's 1, or actually, well, let me denote it instead ab instead of u, because then there's a point c coming up, and so we can have all the same notation. So 2 minus 1, that's a 1. 1 minus -2, careful, that's a 3. And last but not least, 3 minus, well actually, well, you know what, there's a little typo here. It should be, no, this one should be, this component right here should be 0. Okay, 0 minus 3 is -3. Yes, I already have my notes here and I just noticed that typo here. All right. Okay, so we have vector AB. Now let's write down the vector we want to compare it with right next to, which in this case is v. 3, 9, -9. Well, if we look at the components of this given vector, they all have a common factor of 3. All right. So let's factor it out. So that's 3, 1, 3, -3. And well, if we compare these two vectors, they're the same, aren't they? That means the vector v, it's a multiple of the vector defined by the points a and b, and therefore they're parallel. All right. So conclusion. Yes, parallel. All right. All right, now for letter B. There is another point, and the way the point is given is a little weird, but because it's not a numerical point, except for one of the components, one of the coordinates, which is just the x. Y and z are to determine. So they're asking us to find the value of y and z such that 3 points A, B, and C are collinear. Well, what do we mean by collinear points? It means that the 3 points lie on the same line, right? They don't. If at least one of the points is slightly off the line, well, they would form an angle or incidentally a triangle, but in this case, well, we want them to make sure they are on the same line. Well, just a picture here. So if we have A, B, for example, C could be here, and Z in there, and as we can see, the 3 points lie on the same line. That's what it means by collinear. Okay, well, so from part A, we got vector A, B, which is described by 1, 3, -3. Okay. So in this case, well, we want to determine whether the second vector, which contains the point A and C, right, is a multiple of the vector A and B. But how are we going to know if we have no idea about the point C, which is 7, and then arbitrary values of Y and Z? Well, so this is what we're going to do for this point. So we are going to define a vector in terms of variables. So this is the point C, and we're going to define the vector that has initial point at A and terminal point at C. That is 7 minus 1, that's 6. Well, let me write it down. 7, just so you can see where I'm getting this from. So that's this, and let me highlight. 7 minus 1, okay? And then Y, Y minus -2. Be careful with the signs here, because this will become a plus Y plus 2, comma, Z minus 3. This will give us the following vector. That's a 6, comma, Y plus 2, Z minus 3. Okay, well, again, we're going to do the same of comparing vectors, comparing components to determine if we have a multiple, having a vector being the multiple of the other. Question?
Where did you get the 2 for Y plus 2?
Oh, because this is Y minus -2.
Okay.
And so we subtract terminal minus initial. And same here in this case, Z minus 3. In this case, it remains minus. Well, but in this case, okay, let me put these two vectors together. Let me put it, where is my other vector? Okay, yes. So that's the vector AB. If we compare components, rather, okay. If we try to compare, for example, the component, the Y component, well, it's variable, we cannot tell. Then same with the Z component. However, what do you notice about the X component of the second vector? How many times is this potential vector bigger than the first vector we described? 6 times. So that's what I'm going to write here. 6 times the vector AB, that's 6 times 1, 3, -3, which is 6, 3, 6, 18, -18. All right? And well, the thing in this case is that the two vectors are for parallel if they have a component that are multiples, but in this case, what we're going to do, well, from here, 6 equals to 6, which is good. Y plus 2 equals to 18. And Z minus 3 equals to -18. And solving these mini equations, we get Y equals to 16 and Z equals to -15. So the point that will make the vectors collinear, the 3 points collinear, rather the components Y and Z would be 7, 16, and -15. right? That will make the 3 points collinear. All right, let's do one more exercise, and actually we will be done with the section. So this is a word problem with vectors in 3 dimensions. So what do we have? We have a plane flying horizontally towards the north. We're at a 30 miles per hour. Well, that's kind of slow for an airplane, right? I mean, yeah, considering it sways a few tones anyway. I know, maybe it's a glider, I don't know, or one of those RC airplanes, but it's too slow anyway. Well, it's just an exercise, I guess, right? So and then encounters a horizontal crosswind blowing to the west of 10 miles per hour and a downdraft blowing vertically downward to 5 miles per hour. Well, first of all, let's I'm going to use my markers to show you the situation. Well, so let the green marker be the direction of the plane towards the north, and then it encounters horizontal crosswind towards the west. Okay, and then something happens, maybe I don't know, a lightning pushing it down, right? So what we're going to do in this case is find the resultant vector. We're going to add those 3 vectors. But well, first of all, let's write this information given in words in vector notation. Well, so what do we have? Okay, I know this is north, west, south, east. So the airplane vector in green. Okay, and I'm going to do it a little sideways just so you can see the vector. And then the wind was described by the vector in red towards the west. And well, I mean, this one is a 2D plane. There's no way I can write this in terms of, well, for the third vector I'm talking about, it would be a vector popping out of the paper, if you will, right? Well, not popping out, actually stabbing the paper, you know, if the plane is going like this. Okay, so okay, let's write down the vector notation for this. Vector P for the plane. Well, because it's going to the north, there's no displacement in the x direction, only in the y direction, and nothing in the vertical direction. The wind, however, careful here, because in this case, yes, I mean the force is positive in this case for the acting on the airplane, but because of the direction, it's -10. And well, for let's assume it's a lightning striking here. Let's call it the downward force. And this is 0.05 maybe? Negative, right? Because it's going down, right? It's pushing the airplane down. So, well, let's find the resultant vector by adding the 3 vectors. Well, this one is really easy to add. I mean, there's a lot of zeros. -10, 30, -5. All right? Well, now the question is, what's the speed of the plane relative to the ground? Because in this case now, the airplane, I mean, the indicators in the dashboard, well, it's indicating something, but in this case we have other forces reducing the speed of the airplane. Okay, in this case we have a wind towards the west and the airplane being hit from the top. So, well, that's going to be the magnitude of this resultant vector. So let's call this the magnitude, and that's -10 squared plus 30 squared plus a -5 quantity squared. And this adds up to 1025, the square root of 1025 miles per hour. All right.